Hello, this is MAT 221. This is Calculus 1. This particular topic is section 3.3 in our textbook, which talks about the derivatives of the trigonometric functions. So we're going to look at the derivative rules for trigonometry. Since sine, cosine, and tangent functions are all, as well as their cofunctions, are periodic, the derivatives must naturally also be periodic if we were to sketch them, right? So we will discover through our exploration of the sketch of these derivatives that what they're related and how they're related to each other. So let's consider first the sine function. So if we had the function y equals sine of theta or y equals sine of x, it looks something like this in the domain region from negative pi to pi. And if we start by looking and sketching derivatives at different points on this curve, let's start and make a little graph of what the slope looks like. So if I said at negative pi, right over here, the slope looks like it's about, I don't know, I'm guesstimating here, but about a -1 or about a negative number. So then I'm going to plot that point. I'm going to plot the point negative pi, -1, which is going to be plotting my, my derivative curve. So I'm going to pick another point on the curve. Let's pick negative pi on 2. There we see that we had a horizontal tangent line, so the derivative is equal to 0. So I would plot the point negative pi on 2, 0. Then I go at the origin, and I look at the origin right about here, and it looks to me the slope is about a +1 slope. So I would plot the point 0, 1. Then I'd look at pi on 2. Again, we have a horizontal tangent line here, so the slope of the curve will be 0. And I would plot the point pi on 2, 0. And then lastly here at positive pi, the slope looks like it is a -1 slope. So I would plot the point pi, -1. And then if I connect my dots, here would be a graph of the derivative of the sine function. Now what Leibniz and Newton discovered by just doing these graphs, doing these sketches, is they discovered, well, as you might have discovered also, this curve looks very familiar. This actually is the cosine curve. And then they used the limit definition of the derivative that we did in Unit 2, and they actually proved that this is true, that the derivative of the sine function is equal to the cosine function. So the derivative of sine of x is equal to cosine of x. So there's our next rule. There's our first of our 6 trig functions. Let's do the same thing for cosine, finding the slope of the curve at different points. At negative pi, my slope is 0. At negative pi on 2, my slope was a +1. At 0, my slope was 0 again. At pi on 2, the slope was -1. And at pi, my slope was back to 0 again. And again, connecting those dots, what do we notice? So what do we notice here? It's not quite the same. So if I start with a cosine curve, my resulting derivative graph is actually not a sine curve, but it's a reflected sine curve, a curve that is reflected in the line. So we notice that the curve has a derivative that is the reflected sine curve. So our next rule comes from that. Again, Leibniz and Newton used the limit definition of the derivative to actually prove that this is true for every cosine curve. So the derivative of the cosine curve, or the derivative of cosine, is equal to the negative of the sine of x. So it is the negative sine of x. So you notice sine and cosine are related to each other in their derivatives. Now, if we use a little bit of what we know from our earlier classes, we can find the derivative of the tangent of a function by looking at the quotient rule, because we know that the tangent function is equivalent to sine divided by cosine. And now that we have a rule for both sine and cosine, we could just use the quotient rule here. Using the quotient rule, we get low d high, the derivative of sine is cosine, minus high sine of x, d low, which is negative sine of x, over the derivative, over the denominator squared. So that's just using the quotient rule that we did earlier. And then doing a little bit of simplification here, we get cosine squared x plus sine squared x over cosine squared x. And hopefully you guys recognize this numerator. This numerator is one of our Pythagorean identities. There are 3 Pythagorean identities that we learned from the unit circle. One of them was cosine squared x plus sine squared x was equal to 1. And that was true, and that came from the unit circle. We also know that our reciprocal functions, 1 over cosine, is equivalent to secant. So we could leave our derivative of tangent as being 1 over cosine squared, or its equivalent, which is secant squared, which is usually what most textbooks and most authors will use for the derivative of the tangent curve. But both are equivalent because they're equivalent form to the same answer. But for the most part, we do this. We say that the derivative of the tangent curve is equal to secant squared of x. Derivative of tangent of x is equal to secant squared x. Now, we could continue to find the other reciprocal functions in the same way. Derivatives of the remaining trig functions can all be determined in the same way because we know that secant is equal to 1 over cosine. We know that cosecant is equal to 1 over sine, and we know that cotangent is equal to 1 over tangent. So we actually could use the quotient rule and use that the same. But I'm not going to continue to prove them that way. I'm just going to give you these rules. So the next one is cotangent of x. The derivative of the cotangent curve is equal to the negative of cosecant squared. The derivative of the secant function ends up being equal to secant of x times tangent of x. And the derivative of the cosecant function is equal to negative cosecant cotangent of x. So all 6 rules together give us this. These are the 6 trigonometric function rules for derivatives. So let's go through them again. The derivative of sine is equal to the cosine of x. The derivative of cosine of x is equal to the negative sine of x. The derivative of tangent is equal to secant squared x. The derivative of cotangent is equal to negative cosecant squared x. The derivative of secant is equal to secant times tangent. And the derivative of cosecant is equal to negative cosecant x cotangent x. Now, a couple things we want to notice here as we go through. Notice all the functions that begin with a c, the cosine, the cotangent, and the cosecant, all have negative derivatives. And that's one thing I often tell students. Remember, if you're taking the derivative of a c function, cosine, cotangent, or cosecant, their derivatives are all negative values, as opposed to the other 3, which are not. I also want to show you that how the functions are related to each other. Notice sine and cosine go together a lot here. Sine and cosine go together. Notice tangent and secant go together in both of these formulas. You can see tangent and secant are related to each other, and cotangent and cosecant are related to each other. So there's definitely a relationship between those curves. So let's try some examples, bringing together these 6 new rules with some of the rules we already have. So let's try some. The first one is, let's try to find the derivative here. Now here I'd have to use the product rule. Notice I have a function multiplied by a function. I have a sine function multiplied by an exponential. I also have a constant multiple here in front. So here's my derivative. I'm going to bring the 2 sine of x, and that'll be my first function. So I keep the first function times the derivative of the second plus the second times the derivative of the first. Using our new rule would be 2 derivative of sine is equal to cosine. Now, we could pull out a GCF here of 2 and e to the x, but it doesn't necessarily help us simplify as we go through. Next one, let's try this. This is actually using the new rules with cosine and also using the power rule and the constant multiple rule. So let's try to take the derivative. The derivative is equal to, the first term would be 9x squared. Negative 2 cosine of x, the negative 2 would get pulled out to the front. And then when I take the derivative of cosine, that would be negative sine. So the negative negative becomes a positive. So there's my derivative of that second term, that second expression. What about this one? This one is taking the derivative of secant times tangent. So here I'm asking again for the product rule because I have a function multiplied by a function. Doing that, we get the first function, don't do anything to it, times the derivative of the second, which is secant squared, plus the second function, tangent of x, times the derivative of the first, derivative of secant x is equal to secant of x, tangent of x. Again, I could pull out a GCF here of secant of x, but it would not simplify. In this case, even though I end up with secant squared plus tangent squared, that is not one of our Pythagorean triples, so not one of our Pythagorean identities, so it does not simplify. Here, using the quotient rule, we would do low d high. Let's try that again. Low d high minus high d low. In the denominator, the 2 would be 0. Derivative of negative tangent would be negative secant squared over the denominator squared. And again, I'm not simplifying these just yet. I'm just trying to use the rule. In this last expression, we actually have an extended product rule. In other words, when I have a product rule with not just 2 functions, but 3 functions. And for the extended product rule, what we do is we take the derivative of each term separately, leaving the other 2. So let me show you the derivative here. The derivative is, I'm leaving the first 2 functions alone, so I take x and 2 to the x. And then I take the derivative of cosecant, which is equal to negative cosecant cotangent of x. Plus, this time I leave the x and the cosecant alone and take the derivative of the middle term. So it's x cosecant of x, 2 to the x, natural log of 2, taking the derivative of the middle term, plus leaving the last 2 terms, 2 to the x cosecant of x alone, and taking the derivative of the first term, which is 1. So that's called the extended product rule. Again, we could leave it like this. We could pull out a GCF if we wanted to simplify a little bit. Another example here is, let's find the equation of the tangent line to the curve, given this curve at this point. So here's my point of tangency, pi on 3, pi plus 3. And then after we're done, we'll put this on our calculator to illustrate the two, to make sure they look correct on the calculator or on Mathematica. So let's first start and take the derivative. The derivative of the function is equal to 3. Derivative of 6, we bring down the 6. Derivative of cosine is negative sine. Then here's our point of tangency, x equals pi on 3. So we would put pi on 3 in for x, and then evaluate using our trig rules. Sine of pi on 3 is radical 3 over 2. Simplifying this, we get 3 minus 3 radical 3. Now let's put it into the equation of a line. So if we put it into an equation of a line, here's our slope. Y equals the slope, which is 3 minus 3 radical 3. Parentheses, x minus the x coordinate of the point of tangency, which is pi on 3, plus the y coordinate. Now if I graph them on the same set of axes, you can see that this works just fine. So here's our summary. These are all of our rules. Sine is equal to cosine, cosine negative sine, tangent secant squared, secant secant tangent, cosecant negative cosecant cotangent, cotangent negative cosecant squared. Now,